voices like you're good voices.
Good morning, everybody.
Morning.
1915. The world descends into a world war. Approximately, I think it was 6 weeks before the outbreak of the war, a team of German scientists were dispatched to the location inside Russia where the eclipse would have totality, right? They were going to go find a total eclipse. They're going to point their telescopes up there. They were going to look at the apparent motion of the stars and see if light was bending the way that Einstein predicted it was going to. They crossed the border into Russia. They were traveling in the middle of nowhere, Russia, and war breaks out. And the team of German scientists have no idea, right, that anything's happened. And they get arrested by a Russian army platoon, right, that's patrolling the roads. And this is not a good look, right? Okay, the Germans are at war with everybody. They have a wagon full of telescopes, right? Okay, and it's like, no, we swear, we're astronomers. We're going to look at the sky. We're not going to, right? And so Einstein and other scientists around the world spent the better part of 8 months trying to convince the Russians that these were not spies and were in fact scientists. And long story short, there was no data from that particular set of eclipse out there. The next eclipse was in, I think it was 1917 or something like that, and that one was, everything was set and ready to go. I think Cook and some other explorers, somebody was out there in the middle of the ocean. Turned out it was cloudy, so no observations there. But the 1919 eclipse, the pun intended, stars aligned, and they were able to observe the shift in the apparent position of stars immediately around the limb of the sun. In other words, stars that were behind the sun actually appeared to be next to the sun because the light from them was being bent by the gravitational field of the sun. This is an article, right? The Illustrated London News, November 22nd, 1919. Albert Einstein would become an overnight success based on the publication of these results. I've often heard it said it takes 10 years to become an overnight success. Well, in Albert Einstein's case, it took like 15. Right? He was a relative nobody, an obscure German patent clerk, right? Physicist sometimes, and had some crazy ideas about how the universe was put together, but nobody paid attention to that. Well, very few people paid attention to that until the experimental evidence of this eclipse and other things came to light. And he was immediately catapulted into the, not just scientific consciousness, but the public consciousness. There were two famous people at the beginning of the 1920s, okay? They were Albert Einstein and Charlie Chaplin. Like, they were together, right? The pop culture icons of their age. And it was this realization that Einstein was right all along, that these crazy ideas about how space and time change based on a person's motion through them, general relativity, this recasting of how space and time together function, and that gravity could exert forces on something without mass, or gravity didn't have to exist at all. Like what if it's not gravity, like what is it, right? And we still, to this day, will talk about gravity bending the path of light. That's not what's happening at all. What's happening is light is following the curvature of space-time. It's just that space-time gets curved by the presence of mass. Einstein's able to show that Newton's universal formulation of gravity didn't have to exist at all. I don't have the room or the time to get stuff like this set up, which is why I'm grateful for YouTube. This is a physics teacher showing his students. He's got like a piece of like spandex, really stretchy fabric. And do you see how he's thrown a weight here in the middle? So this thing is like, the stretchy fabric is like space-time. Think of a flat sheet as empty space-time, no mass in it. And then you throw a mass in there, like say the sun, okay? And you see how it bends space-time out of the way? Well, what he's gonna do, there's no volume here. What he's gonna do is he's gonna take some like marbles and things. You see how if he just lets one go, it drops towards the weight? The marble is forced to follow the curvature of space-time, regardless of what it's doing, okay? And like all physics teachers, he's talking too much instead of demonstrating what's going on. So he's gonna take one of those marbles and he's gonna give it some tangential velocity here. Yeah, keep talking. Good job. Okay, so if he drops it straight towards it, right, it falls straight towards it. But give it some sideways velocity, and what does that marble do? It orbits, right? It orbits around that mass, not because gravity is pulling it down, but because it has no other choice but then to follow the curvature of space-time. The Earth is not in orbit around the sun. What do all objects do if they are not acted upon by an outside force? What is their path? It's a straight line, right? Newton's first law, the law of inertia, an object at rest will stay at rest, an object in motion will continue in motion unless acted upon by an outside force. With Newton, we needed an outside force to pull it into a circle, because a circle is accelerated motion, so there needed to be a force, and the force was gravity. According to Einstein, gravity isn't the thing. It's the curvature of space-time that's the thing. And the Earth isn't orbiting the sun. The Earth is following a straight path in curved space. What we see as an orbit is the Earth moving in a straight line in a space-time that has curvature. And if that either hurts your brain or you're deciding that this is too much and you want out of your major, whatever the case may be, realize that you do this all the time, every day. When you drive here, let's even just pretend that there were no buildings in the way and there was a straight road between wherever you live and this campus. You would not be traveling in a straight line. Why not? The Earth is curved. You are moving on the... When an airplane flies from San Francisco to New York, it does not fly in a straight line because in fact, where are we? The Sierras over there? New York is that way. Why am I pointing down and in? Because the Earth curves. Planes have to correct for this. If you tried to fly from San Francisco to New York, you'd have to fly through the ground, right? The plane has to follow this curved path over the surface of the ground. We call it a straight line, but it's not. It's a straight line across a curved surface, if you want to think of it that way. Think of an ant walking on the outside of a bowling ball. It can't move in a straight line. It can only move along the curve of the surface of the basketball. We are much the same way. The problem is, with all of these sort of pictures and ideas about what space-time looks like, this is a lie. That's a two-dimensional sheet that is bending into the third dimension. Space-time, x, y, z, and t, is four-dimensional. And so where do the curves happen? In the fifth dimension, which gives rise to that phrase that comes out of so many kitschy science fiction things, right? Going to the fifth dimension, whatever, okay, fine, right? So to visualize this is always a cheat. Unless you just actually look at what the universe does. And then you're not cheating at all, you're taking observational data. This is an atomic clock. I know it doesn't look much like a clock, but it is, okay? And in the video that we saw in lab, they were talking about these clocks and how they use cesium, the vibrations of a cesium atom, to figure out what 1 second is. The point of these clocks is that they are hyper accurate. They are so accurate that they can be affected by the curvature of space-time. Again, Einstein's general relativity tells us that space and time are affected by the presence of mass. The Earth is curving space-time around it. The moon is following the curvature of space-time around the Earth. The further down in the curvature, the closer to the surface of the Earth, the slower time moves compared to distances that are further away from the Earth. And that time discrepancy can be measured if, let's just say, we happen to, launch an atomic clock onto a satellite. Can be done, has been done, and it's something you use probably all the time without knowing it. Because TikTok, Instagram, Facebook, and all the others, Apple, Google, Samsung, they're all tracking you. What does your phone do? If I asked you to go somewhere in town, right, you would just ask me for the address. Rather than me give you a set of directions, you would just put it into Google Maps and take me there. How does that work? Magic or GPS? The GPS system, the Global Positioning System, consists of a series of satellites. This is the one with the cover off. You see all those antennas in there? Those are all various antennas for various things, but in the heart of that satellite is an atomic clock. The way that you know where you are in 3D space is you collect a minimum of 4 separate signals. If this were 2-dimensional space, you'd need 3 points, but in 3-dimensional space, you need 4 points. So 4 different satellites, all moving independent of each other, in different parts of the sky. Figure out how far away you are from that satellite. Do that for all 4, and where all those distances intersect is your location in 3-dimensional space. How do you know how far away you are from that satellite? I mean, you get a tape measure out? What does your phone do? What's the one thing we can all agree on, regardless of where we're looking and how fast we're going? Speed of light. So get that satellite to send a radio signal. How fast do radio signals travel? At the speed of light. They're a light wave, right? On that radio signal, you encode information about what time it is on that satellite. That time information comes down. Your phone knows what time it is. It knows atomic time, which is standardized across the world. And so your phone compares the known time here on the surface of the planet Earth with the time that that satellite said it was, figures out how far away that satellite was, does it for all the other satellites your phone can see, puts all that information together to give an accurate representation of where you are on the surface of our planet. Longitude, latitude, and elevation. 3-dimensional coordinates. That only works when you correct for the relativistic changes to time that take place because we are on the surface of the planet and the satellites are not. And for the relativistic changes from the satellites moving with respect to us. Without the relativistic correction, GPS could be no better than, this is where you are plus or minus a kilometer. Can your GPS give you turn-by-turn directions if it doesn't know where you are within like 0.6 of a mile? Like your GPS knows what lane you're in, right? I mean, it probably knows where your rear end is sitting right now. We've got satellite systems, the surveyors, our engineers, our civil engineers got survey systems here in the back room. They can tell you where a point is on the surface of this planet Earth to within like 3 millimeters. You want to have an argument with your neighbor over whose dirt that is? We can tell you. It's crazy good how well we can pinpoint something on the surface of this planet, right? It doesn't work unless you take into account relativity. I can't think of a better situation that shows in real time how relativity works. It's crazy math. This is a depiction of the GPS system. Right now, I think the GPS system consists of I can never remember this number, 28? 29, 36, they deorbit and they put new ones up. They're in a constellation that guarantees that no matter where you are on the surface of the planet, there will be a minimum of 4 satellites above the horizon. Poles, anywhere you want to go, you will always have 4 satellites above the horizon. Usually at the mid-latitudes, like where we live, there's like 12 to 17 of them always above the horizon. So you get lots of data, more accurate fixes for where you are, that kind of stuff. The hyper-accurate ones require sort of larger antennas to pick up better signal. Our phones don't have really big GPS antennas in them. We don't want to carry around that backpack. So our phones do cheat a little bit. They not only get a GPS signal, but that's almost secondary now to the other signals that they get, which are from the cellular towers. The cellular towers are measured to a very high degree of accuracy of where they are, and then your phone can do a very similar thing like it does with GPS. It knows which tower it's at, it knows the location of that tower, knows how long it took for a signal to get to the phone, again, traveling at the speed of light. That it can do really rapid math. So it does that, and that's called assisted GPS, where it's using the cellular network. It also uses Wi-Fi base stations to triangulate where you are, like inside buildings. Like, I don't know if you've ever noticed that GPS works inside. Normal GPS doesn't work inside. Buildings get in the way of the radio signal. But inside, you can hit the cell towers and the Wi-Fi antennas. And if the operators are good about locating those things and every device has a section in it where you can give its precise location. If those are set up well, then the machine learning can get a hyper-accurate representation of where you are, even inside buildings. So the relativity part really comes from space, but you can take advantage of the science of it to get really good location information. All right, direct observational evidence of general relativity comes when we start looking at the big universe. Gravitational lensing is what happens when light is bent around foreground objects. I'm going to lower the lights a lot here so we can see the detail on these pictures. So, it can be kind of, I don't know, a little bit difficult to see here, but there's a really bright object right here, and then again, another really bright object right here. These objects are actually between us and what we're trying to see. What we're trying to see, do you see these streaks? These kind of circular streaks that are around the outside. There's one like right there. Around this one, there's a streak there and kind of a streak there. What those streaks are images of galaxies that are behind these very massive foreground objects. The light from behind these quasars is being bent, and we're seeing the lensing effect that gravity is having on this light. Just like light would bend as it goes from one medium to another, which we studied in optics, gravity can have that effect on light as it travels through the vast distances of our universe. And we can see things that are actually behind. Here's a false color. So what they've done here is they've colored in blue the things that are all part of the same object. It's just that its image has been stretched out and around. You've got this cluster of stars and galaxies that are sitting here between us and this blue thing that happens to be behind there. And by looking at the spectral lines that are coming off these things, we can tell what light belongs to what. And everything in blue here came from one thing, which again just happens to be behind that incredibly dense cluster. Again, this wouldn't happen without special or general relativity. This is quite frankly my favorite one. It's called the Einstein cross. Okay, there's a dense object here in the middle that we can't quite see, and these 4 dots right here are all images of exactly the same thing that's behind this massive object in the center. It's called the Einstein cross, okay? And all 4 of those dots are the image of the same thing. It's just the gravity of the foreground object is causing us to see 4 versions of the thing instead of just one. Again, wouldn't happen without the curvature of space-time and general relativity. This is a simulated picture of the famous museum that's at the Smithsonian on the Washington Mall. This building was donated by France, I think, and they hauled it brick by brick in the late 1800s over the United States and rebuilt that. For some reason, I guess we wanted one. But this is what would happen if you dropped a very massive object between you and that building. This is an accurate simulation of what would happen to the curvature of space and time and what the light would look like if there was like a micro black hole that was sitting between you and that building. Of course, you would be sucked in, the building would be sucked in, Congress would be sucked in, that might be good. In terms of what the light would look like and how it would be bent, it's not, I show you this so that you can see that it would not be straightforward, right, okay? These curves, this warping, this changing of space-time is very complex and gives rise to some very trippy things. This is the Matterhorn, and if you had dropped something very massive like a neutron star in front of you and the Matterhorn. Which brings us to quite possibly pop culture's most well-known feature of general relativity, which is black holes. Black holes were not discovered by Einstein. They were discovered by a German physicist by the name of Schwarzschild. He went into World War I. He was a patriot. He supported the German cause, and he went into being an artillery officer in World War I. And he was responsible, because he was a physicist, he was responsible for calculating artillery trajectories, okay, for launching the artillery shells. And that was very boring work for somebody that knew how to do general relativity, right? He'd been reading Einstein's papers and all that kind of stuff. And so in his field notebook, in between calculations for how to bomb the British soldiers on the other side of the trenches, he was doing relativity problems. He was playing around with the equations of general relativity. And what he discovered is that you could get to a curvature of space-time that was so curved that not even light could get out of the curve. A well that was so deep and steep, so to speak, that light could not escape. And he called it a dark star. But it later became known as a black hole. And this is a simulation of what it would look like to approach the event horizon of a black hole. Starting out and away from the black hole, first of all, we would notice a lot of actual bright light, because there's actually a lot of material that are around black holes and being sucked in. But we would approach and we would see swirls of light. That motion isn't the black hole itself, it's the curvatures of space-time as the black hole rotates. As we get closer and closer to the black hole, time for us would slow down. Well, time for us would look like nothing's happening, but observers outside looking at us would see us fall towards the black hole and time slow down, and we would actually freeze as we hit the event horizon. This is coming right up on the event horizon, the point of no return, and the rest of the universe kind of gets very stretched out. And at the event horizon, you hit a point of infinite light, where all the material that is falling into the black hole is kind of piling up. It's hard to say what would be on the other side of the event horizon. There's all kinds of theoretical predictions, but there's no way to measure what's going on inside there because we can't get any information out. Once information, light goes into a black hole, it's not coming back out again. More than likely, the material that falls in continues to swirl. You hit the universe's biggest firewall, literally a wall of flaming hot plasma on the other side of the event horizon. One of the things that people get wrong about black holes is they don't realize that every black hole that we know about rotates. Stationary black holes are a theoretical construct. All black holes have some sort of angular momentum associated with their creation, and so none of them sit still. But if we were to be able to approach a stationary black hole, one that is not rotating, we would see this, okay? So all of what you just saw were like background stars of the universe, right? Just the stars in the sky, right? And the black hole in between that, we can't see anything because no light comes in or out of it. But we can see the warp that is caused by that black hole. And as we get closer and closer to the black hole, space and time get more and more warped until when we hit the event horizon, space is infinitely contracted. Like literally the entire universe is right there, okay? And time gets infinitely dilated and all kinds of things. What is more correct, okay, would be being near a rotating black hole. This isn't a simulation of actually like approaching a black hole. This is just kind of standing next to it and watching as the black hole rotates. Do you notice anything that's really strange here? How is it spinning? Both ways. Do you see it? Stars are orbiting counterclockwise, but some of them are going clockwise. There are counter-rotating bands of space-time around a rotating black hole. Yeah, my brain hurts too. Okay? So, black holes were thought to be there. We had a lot of indirect, oh, by the way, this is what happens if you send a black hole in front of the Earth. The bottom here, okay? That's its position, but this is what it would look like if a black hole came between you and the Earth, assuming the Earth didn't get ripped apart by the black hole in the first place, right? Okay? But again, so black holes were thought to exist. We had a lot of sort of anecdotal evidence. We knew that stars were being pulled into strange orbits without being able to see the thing that was causing the stars to deflect, right? So you kind of look at how stars are being deflected and you go, well, there's got to be something there, but we can't see it. It must be a black hole. So how do you like get a picture of a black hole? Well, we actually have taken a picture of a black hole, and I need to get it into my slides. I'm sure everybody's seen it. But perhaps more important for physicists, other than just like a direct picture of a black hole, which again, you don't take a picture of a black hole, you take a picture of the stuff that's being pulled into it, all right? For a physicist, we need something better than that. And what we got in 2015 was something called gravity waves.
Gravitational waves were predicted by Einstein almost 100 years ago.
A gravitational wave is a ripple in the fabric of space and time. It's produced somewhere in the distant universe and travels across the universe.
When any massive object moves, it's changing the nature of space-time. That's what Einstein told us.
So you have a motion that stretches space in one direction and compresses space in the other direction.
Nobody really believed at the time of the prediction that you could ever detect them because the size of the effect is so small.
It was what we call a chirp, and it was strong.
Everybody thought it was a fluke. It was too good.
And I thought, my God, this looks like it's it.
Oh my gosh, this is real. It took us 25 years and 2 detectors to finally detect a gravitational wave. We have interferometers, one in Hanford, Washington, one in Livingston, Louisiana, to detect the stretching and compressing of space.
We literally look for changes in the space-time distance in our instruments as the gravitational wave goes by.
And the gravitational wave pushes them together and apart by 1/1000th the diameter of the nucleus of an atom. No wonder it's taken so long to pull this off.
However, what's even more remarkable about this is what we detected.
We have observed gravitational waves from two black holes forming a larger black hole.
For the first time, two black holes
Spiraling together, coalescing, merging, creating wild oscillations, a storm in the fabric of space and time.
They're moving at the velocity of light, damn near that velocity. 30 solar masses moving that fast. I mean, they're putting out incredible amounts of energy.
and when they collide with one another, they produce a bigger black hole, but they also produce gravitational waves. And in that process, about 3 solar masses just disappears and goes into gravitational waves.
Oh, it's going to be amazing. We have always said that this is going to be a field called gravitational wave astronomy.
Gravitational waves carry information that you can't get from any other way. A supernova, 2 neutron stars colliding, even the Big Bang itself, the beginning of the universe, all produce gravitational waves.
This first detection by LIGO is the very first step. It's just the start of the story nature is about to tell us.
I would love to see Einstein's face. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's a miracle.
So these waves that are set up, right? Kind of like waves on the ocean are waves in the fabric of space and time. This isn't light, right? This is the actual fabric of the cosmos that is oscillating as black holes merge, neutron stars merge. These are the most energetic events that we can conceive of in our universe. And we now have the ability to not just detect them, right, to see that they're there, but actually measure what's going on, right, as these bodies collide. Not only does it give us a new way of looking at the universe, it shows that Albert Einstein was right. That these ideas about how space and time are affected were correct. Granted, special relativity is special in the sense that it is merely theoretical. You can't observe special relativity because everything accelerates. You've got to get stuff moving in the first place. The general relativity is what we use as the proof of what's going on. We've observed general relativity to be happening. We've measured its consequences. The special relativity, though easier to do mathematically and perhaps easier to understand, is not something that we would observe ever in the universe. Because it's special, because it's limited. But that doesn't take away from the fact that space and time are affected by relative motion, by mass, and by what's going on in the fabric of space and time itself. This is the first detection, and they have taken the wavelength and frequencies of these gravitational waves and converted them into the audible spectrum. Gravity waves do not make noise. But if they did, this is what they'd sound like. And then sped up. A heartbeat. A static with information that is going to let us look back to the very beginning of our universe. We are going to, we're going to park our exploration of the universe right there. And we are going to actually come back to where we left off with optics. Because remember, relativity is a bit of a tangent. It's a decent one, but we have to talk about Einstein's other papers that happened in 1905. So we've just finished this mind-bending, literally, exploration of the consequence of keeping the speed of light the speed of light. And now we need to talk about the other things that Einstein did. Because Einstein didn't just reinvent our concept of the large-scale universe. He reinvented our concept of the small one as well. Remember the 4 papers of the miracle year of 1905, 2 of them had to do with special relativity, and then there were 2 other papers, one on Brownian motion and one on the photoelectric effect, that would bring Einstein notoriety and fame. But we need to talk about something called black body radiation before I can get to the photoelectric effect. Black body radiation is a catch-all term for the emission of light from a perfect light source. A black body is kind of a weird name for something that gives off all the wavelengths of light, everything, the entire electromagnetic spectrum. And the reason it's called a black body is because, in theory, it can also absorb all of the frequencies and wavelengths. So it can suck in all the light. It's not a black hole. We're just saying that it can absorb all that energy and it can release all that energy. So an ideal black body would shine with all the light rays, but it could also absorb all the light rays. So a German physicist in 1903 by the name of Max Planck, yes, that Max Planck, if you've ever heard of the Max Planck Institute over in Europe and many other places that are named after him. He was a very famous physicist in his day, but probably his most famous discovery would be Einstein. It was Max Planck who gave Einstein his first job as a physicist. It was Max Planck. Max Planck's, I believe it was his son-in-law, had met Einstein and told his father-in-law about him, and Max Planck gave Einstein a job in physics when nobody else would. Kind of rescued Einstein from the patent clerk position, right? Kind of wasting his time at a patent office, and gave him freedom to develop the general relativity. Max Planck was studying black body radiation. He was setting up experiments. He couldn't get, of course, all the wavelengths of light, but he could get most. And he was doing it by staring at basically hot things. He would heat up ovens, metals, objects, get them to glow, and he would study the radiation that was coming off them in an attempt to understand how things made light, what the light consisted of, what was light made of. It's the early 1900s. We know Maxwell's equations. We know that these things are waves, right? And so Planck is trying to do experimental work in figuring out what these wavelengths are. He was actually really interested in what the energy was that was contained in light. And so he was doing these experiments where he was measuring intensity and wavelength, and how intensity changed with wavelength depending on what part of the spectrum you were looking at. I don't want to get into a lot of details because a lot of them are very boring. But the big deal, okay, the big deal came in this representation right here, okay? Classical physics, the physics of Newton and Maxwell, everything up to that point, gave a prediction for what the intensity should be at various wavelengths that are coming off of a black body, off of something that's glowing because it's hot. This red curve right here is what the classical, again, Maxwell and Newton and everybody up to this point, all weighing in on what light should be doing, predicted that as wavelength got smaller, intensity should go up for these black bodies. The blue line, though, is what Planck is measuring. okay? So what we have here is a discrepancy between our observed or experimental data and what our models or our theories predict for what should be happening. And this was where Max Planck was most excited. He was trying to investigate this discrepancy. And try as he might, okay, he was struggling with the information that his experiments were telling him. No matter what he did, no matter how he looked, he found that the energy coming off of black bodies had a kind of a fundamental amount, a resolution beyond which he couldn't probe anymore. And it wasn't because his equipment wasn't good enough. It's just that as he measured it, he discovered that the energy coming off of these black bodies came in very discrete packets or chunks. Energy had something to do with frequency. He knew that. And if we can go back to Roy G. Biv, put it over here. Which of these colors are the high frequency short wavelength end of the spectrum? The violets, right? The blues, indigos, and violets, right? So here's your high frequency, right? Here's your low frequency. So when Max Planck was looking at, say, red light, he would notice that the chunks of energy were small compared to when he was looking at bluer light, and those chunks of energy were larger. And he couldn't, no matter how he tried sliding between all the different colors and going in different parts of the spectrum, he was always finding stairs where he expected to find a wheelchair ramp. My analogy, not his. So Max Planck wanted to find a nice, smooth connection between the wavelength or the frequency and the energy that was coming off of his black bodies. A infinite number of degrees, right? As you switch from one frequency to another, the energy should smoothly connect between all of those things. And that's not what he discovered. What he discovered over and over and over again is that the energy was more like climbing the stairs. When you climb the stairs, think of like a really wide stair step, right? Okay? You step up and then you have to walk, and your potential energy stays the same for a little bit before you step up again. All of your energy changes when you go up the stairs are very abrupt. You have an energy and then boom, you change your energy suddenly, and then you have another energy, boom, and you change, right? Unlike a wheelchair ramp, which would have a nice, smooth, continuous change in energy all the way up. So Planck is getting the stairs, even though he expects to find the wheelchair ramp. And the stairs all had a height, okay, that was equal to this. And he doesn't know what to make of it. He can't really kind of figure it out. He doesn't know why this is happening. He trusts the theory. He knows that something should be happening correctly there. And he tries to come to grips with it by doing the thing that any self-respecting scientist would do. Hold on a second, I gotta find my lecture thing. Where is it? No, not that one. He does a thing that any self-respecting scientist would do, and he publishes his data, right? He doesn't know what to make of it, so he's like, I gotta get this out to the wider scientific community so that other people can see this, so that they can take their best stab at my data and see what's going on. Well, he publishes his work, and everybody goes, so? Like, they're not impressed by it at all. And he doesn't know what to make of it. And so he decides to just park it on a shelf. He kind of puts it up on his library shelf and forgets about it. All right. Now we come back to, finally, where we left off in our lecture on the history of light. I don't know if you remember, But I did start, okay, this whole second half of the semester really with what is light? And we stepped through, we discovered how Newton said light was a particle. And then Thomas Young came along and said, no, light's a wave. And then black and white photography came along and said, no, it's a particle. And then Maxwell came along and said, no, it's a wave. And then we spent like 3.5 weeks of our life dealing with the wave-like nature of light. Well, it should come hopefully as no surprise that Albert Einstein weighed in on the debate as well. I mean, the poster child in physics for who wants to know how light works is Albert Einstein, right? And so it's what drove him. He needed to know what it was, how it worked. It helped him reformulate and discover that the universe is a much grander, more elegant thing than we could ever possibly imagine. And so Albert Einstein does weigh in on what light is. This is an actual picture. Okay? This is a picture taken, I think in the late 30s, early 40s. Of the photographer taking the picture said, "Hey, Doc, give me a face." And that's what he did. Right? So that's an actual thing. Albert Einstein, in 1905, did special relativity, did Brownian motion, and then also gave the correct explanation for something called the photoelectric effect. 4 papers, 1 Nobel Prize up for grabs in physics. Out of those 4 papers, and spoiler alert, he did not win for general relativity, even though it was general relativity that would make him famous. Of the 4 1905 papers, do you want to guess which one he won the Nobel Prize for? It's not relativity and it's not Brownian motion. It was for the photoelectric effect. Here it is. Prepare to be underwhelmed at first.
And the evidence can still be seen today in the behavior of a gold leaf electroscope. When the electroscope is charged, the leaf rises and stays aloft until it's hit by a beam of ultraviolet light. An ordinary piece of glass transmits visible light, but it blocks the high-frequency ultraviolet light. When it's interposed, the electroscope doesn't discharge, but when the glass is removed, the leaf falls again. This proves that the ultraviolet light does the job, and it's called the photoelectric effect.
What just happened? What did the light do? Make the thing move. What was the thing? It was a gold leaf electroscope. In other words, it was something that detected the presence of charge. So they charged up a piece of metal and then shined a light on it. And what did the light do? It discharged the metal, right? That's the photoelectric effect. But it goes one step further. Not any kind of light can do it. Did you catch the kind of light that they were talking about in the film? It was ultraviolet, right? The glass that they put in front of it blocked UV. It let the visible light through, but ultraviolet was blocked. And when the ultraviolet was blocked, there was no discharge. So apparently, lights, so number one, it's kind of crazy that light can discharge a metal, right? Because light doesn't have a charge, it doesn't have a mass. What the heck is going on here? Number two, why is it only certain frequencies and wavelengths of light that can do this? Why can't all light do this? The photoelectric effect was well known before Einstein's birth, okay, but did not have a satisfactory explanation until Albert Einstein weighed in. And it would be the explanation I'm about to give you that he would be awarded the Nobel Prize for in 1921. It was the 1920 Nobel Prize awarded in 1921, along with the 1921 Nobel Prize, because no Nobel Prize in Physics was awarded in 1920. The deliberations of the Nobel Committee are always kept secret. Nobody ever knows kind of who's nominated or what the committee talks to each other about. And so it was a bit surprising in 1920 when the committee came back and said there will be no prize this year. Of course, everybody wanted to know why, but the committee wouldn't talk. Members of the committee, decades later, when asked, would not break their silence, but would suggest that because Einstein was Jewish, that they couldn't award the prize in that year. There was several anti-Semitic people on the Nobel Committee that year, and there was no prize awarded. That is a matter of historical debate, right? We do have the testimony of some of them not telling us exactly what the deliberations were, but insinuating that was the case. Whatever happened, the Nobel Committee decided that in 1921 they would award the 1920 prize to Albert Einstein, not for relativity, not for the general relativity that made him famous, but for the photoelectric effect. So in spite of their racism, it was a new committee, by the way, in 1921. In spite of the racism, the Nobel Prize is an indicator of what the community thinks is important. And so to have the prize for the photoelectric effect be given instead of relativity really underscores the impact of what I'm about to tell you. Albert Einstein looked at this and said, okay, light's a wave. So if light's a wave, energy, the amount of energy it takes to knock a charge off of the surface of this metal should be a function of amplitude. The energy of a wave is carried in its amplitude. The bigger the amplitude, the more energy you have, knock charges off of the metal. But amplitude does not depend on wavelength or frequency. For a wave, amplitude is just amplitude. It's the amount of energy you're putting into the wiggle. Right? The frequency and period can be whatever they want, and you can make the amplitude as big as you want. And so this means that under the wave-like nature of light, as indicated by James Clerk Maxwell in his equations, any frequency and any wavelength of light should be able to discharge a metal independent of its color. Make it bright, charges will come off. That is not what is happening. And so Albert Einstein said, okay, if light's not a wave, then what's the other choice? Particles. Okay, if light's a particle, I need a way to describe its energy as a function of its frequency or color. Einstein doesn't have to do very much work because the work has already been done. Who did it? Max Planck, right? Max Planck had been studying black body radiation, had discovered the energy coming off of these black bodies coming off in discrete chunks, or in Latin, the word is quanta, little bit, but didn't know what he had found. Albert Einstein, reading Max Planck's work, realizes almost instantly what Planck has measured. Planck has measured the energy of a photon. E equals HF should be the equation that is written in every comic strip you see on the board behind every physicist in a documentary. Not E equals MC squared. E equals HF is the equation that would rock physics to its core. As amazing as relativity is, this is way bigger And it seems so innocuous. It seems so innocent. It seems so simple. But what this did was arm Einstein with the ability to explain the photoelectric effect and reinvent how we understand light. This is how it goes. The energy of light depends on its frequency, the color that it has. The higher the frequency, in other words, the bluer or more ultraviolet the light becomes, the higher energy a photon has. The more energy a photon has, the more likely it is to be able to knock a charge off of a charged piece of metal. This is why low frequency, long wavelength, redder types of light cannot discharge metals. No matter how bright you make them, they will not discharge metals because they lack the energy per photon to be able to knock charges off the metal. But you can take some of the dimmest ultraviolet lights you can find and shine that light onto these metals, and the charges will jump off like rats from a sinking ship. They will just fly off of that metal. It would be like, it's kind of like bowling. And if you're bowling with red light, it would be like bowling with ping pong balls. You can throw thousands of ping pong balls down the lane, and are the pins ever going to knock over? No, like one out. I mean, if you shove, a million ping pong balls down the bowling alley, it's going to knock everything over, right? But like one at a time, throwing ping pong balls at it, you're not going to move those pins at all. No matter how many balls you threw, they're just not going to go anywhere, right? But one bowling ball, moving relatively slowly, can knock them all down. Blue light is like the bowling balls, okay? It only takes one, and it's got enough energy to do it. Red light is like ping pong balls. The energy per photon is just too small to be able to pull it off. Why is this so amazing? Why is this explanation worthy of a Nobel Prize and relativity isn't? Many of us physicists think the Nobel Committee in 1921 didn't understand relativity, and so they picked the one they did understand. But in hindsight, their choice was correct, because again, this one shifted physics more than relativity did. You cannot explain the experiment without knowing, assuming, and taking for granted that light is what? Light's a particle. You cannot describe the photoelectric effect using Maxwell's equations. It simply doesn't work. The predictions aren't there. It just doesn't happen. Again, Maxwell predicts red light, just make it more intense, it'll discharge. That's not what happens. Newton and Einstein versus Maxwell and Young. Experiment. Young did the experiment, right? Light is a wave. It interferes with itself. Particles can't do that. We get interference phenomena. We get diffraction. That's real. The photoelectric effect cannot be explained unless you conceive of light being a particle. The wave-like formulation doesn't work. So what is it? Both? Can't be both, right? Here's a cartoon, okay, from the 1930s. Okay? It's trying to depict a photon, right? Okay, moving along. But you notice how this particle-y thing, which apparently has a cape for some reason, is also kind of wavy, right? This kind of captures sort of the state, right, of physicists following Albert Einstein's photoelectric effect paper, following Maxwell's, like, it's just, nobody knows what's going on. How can something be both? It's got to be one or the other. Or if it's both, that means our understanding of it is flawed. You can't have two separate, like for physics, I mean, maybe for politicians this is okay, but for physicists we cannot have two different sets of rules. We just simply can't. It's not in our nature. We are trying to discover the fundamental ways that the universe is put together and how it works, and if we've got two different ways of doing it, we don't understand something. By golly, we have the hubris and the arrogance to go, we can figure it out. So, how do you resolve paradoxes? Logical or otherwise? You do experiments, right? But we've already done experiments. Okay. So, is there an experiment that we can do that maybe can show us both? Right? This is the question. So here's the experiment that was conceived of in the 1920s and first done in the 1930s. We are going to take a double slit. Okay, so immediately, double slit means we're testing what? Wave-like nature, right? Interference, all that kind of stuff, right? We're going to take a double slit, and we're going to shine light on that double slit. We're going to put a screen behind it. We're going to see what the pattern of light is on the other side. But we are going to take that light and one photon at a time, we are going to send one photon at a time towards that double slit. One photon at a time. What are we taking advantage of now? A particle, right? Because we know the energy of a photon. If we dial in that energy, we know we got a single photon coming out, right? And so we're going to take a single photon, we're going to send it towards a double slit. I got you now. Right? What are you going to do, particle? What are you going to do? Got to choose. Got to pick. So this is what happens when you send about 100 photons through a double slit and measure where they impact on the screen. What do you get? Waves or particles? It's particles. It's like combining the black and white photograph together with the double slit, right? It's like the perfect meeting, right? Well, here's what happens when you send roughly 1,000. And then 10,000. What is light? I have no idea. I can tell you that one at a time it acts very particle-like, has specific energy, specific location, but put it together in groups, and it seems to get together and form a wave. So is it a wavicle? A party? I mean, this is the kind of result that gets a physicist excited, right? Because it's like, oh, we have no idea what's going on. I have job security, right? Okay? Because if we can explain it, then nobody needs us anymore, right? We just need bigger words. But like, it's supposed to be one or the other, right? The experiment was supposed to be. For the last 3.5 minutes, I've been lying to you. For dramatic effect. And this is the lie. I told you that was the picture when you sent 100 photons towards a double slit. Those aren't photons. Those are electrons. What's an electron? A charged what? Because what happens when you send more? And even more? What's an electron? I have no idea. Because something I thought was a particle is now behaving like a wave. There's a big difference between a particle of light, a photon, and an electron. What is it? What does an electron have that a photon doesn't? Charge and? How can something with mass do that? I can walk around with the cognitive dissonance in my brain that light is like a particle and okay, fine, but it's light. It's like mushy, right? Like light's just everywhere, right? Right? Okay, fine, it's both, whatever, right? Physics, smoking dope, whatever. But electrons? I mean, that thing that like holds atoms together and chemical bonds and stuff? It's got charge, it's got mass, it's got place. What the heck is it doing having a wavelength? What is it doing interfering with itself? Nobody asked me if this was okay. You are looking at the birth of quantum mechanics, not the far side, but the idea that is going to become quantum mechanics. E equals hf. Today called the Planck-Einstein relationship or formulation for the energy of a photon is the foundational and fundamental equation of quantum mechanics. A lot of people say, it was Schrodinger's equation, let's do the cat in the box. And it's not, okay? This is where quantum mechanics got started. Albert Einstein invented relativity and quantum mechanics. Now, of course, the way we understand it nowadays would not be Einstein's doing. It was a lot of scientists that got together to grapple with the impossibility of wave-particle duality. It will be something that we are going to grapple with for like the next 2 weeks. Is trying to come to grips with this idea that things can be both particles and waves at the same time. And we are going to grapple with it in the photoelectric effect, and then there's going to be uncertainty principles, and they're going to be uncertain a lot for a lot of things because quantum mechanics does not make sense. Relativity makes sense. Relativity is hard. Relativity is difficult because of time and space and proper time and proper, I get you, right? It can be confusing to navigate successfully a homework problem in relativity. But at its fundamental, relativity feels explainable. If you really believe in the postulates, you can explain it to somebody. It's weird, but it's explainable. Quantum mechanics isn't. Quantum mechanics will fly in the face of every intuition you have about how the universes work. And as a physicist, I solemnly swear that I would not teach you quantum mechanics if it didn't work. Physicists, there's some physicists, go talk to Mr. Agsdale, he likes it. But quantum mechanics is fundamentally, like it's built into it that you can't understand what's going on. It just is. And you'll see what I mean as I take you through it, okay? Built into it is a randomness and inherent, like, is there a gut feel? Can you gut feel your way through quantum mechanics? Not even physicists can do that. And we deal with it all the time. It flies in our intuition, and it's just not nice. So let me leave you with just some videos about the photoelectric effect. We're going to do our best in the Physics 2 series here, Physics 2B, to ground you in reality, because there's about 2 semesters worth of content that I could teach in the next week and a half, right? But thankfully, you don't have to go there. But by the time we're done, I hope you're going to understand chemistry. Those of you that took it are going to go, oh, why didn't we just say that? And for those of you who haven't taken it yet, you're going to go, I know where you're going, right? But let me leave you with this idea of the photoelectric effect. This is a visualization of kind of what's happening with photons of light.
An electron in a metal lacks enough energy to escape by an amount called the work
It's over there on the right.
But if an electron absorbs ultraviolet light that arrives in a bundle having the energy given by Planck's formula, then the electron can gain more than enough energy to escape from the metal. If that's the case, it can come out with kinetic energy equal to h times f minus the work function. This is called Einstein's photoelectric effect equation.
Who got him the Nobel Prize. That equation right there, okay, is, we'll put it in a box, okay? You have the energy of a photon sitting right there. You have the kinetic energy of that photon left over after the charge has to get up. I like to think of work functions and photoelectric effect being a little bit like a fence. Okay? If you have a tall fence, right, and you can't climb the fence, you can't get over the fence, right? No matter how fast you run at the fence, you're not going to get over the fence. What do you need to get over the fence? A ladder, a boost, something, right? Okay? And so what the photon does is it comes along and gives you a ladder, right? It lets you overcome your lack of potential energy or ability to get potential energy. And so let's say that the fence is, 8 feet high, but the ladder's 12 feet high. You're getting over the fence with extra, aren't you? Well, that extra will turn out to be extra kinetic energy. If you just barely make it over the fence, then you're not going to be moving, right? But if you go too high, you're going to have some extra energy on the other side and be able to move. That's what's going on in the photoelectric effect. Photons that don't have big enough ladders can't help the charges off, right? You need to be a photon with enough energy to give that thing a boost, to get it over the fence of the metal that it's in. We'll pick up with that, and I'll give you an example next Tuesday, right? Because I think you've got relativity homework due this week, right? If I don't see you tomorrow, have a fantastic weekend.